Imagine a computer so powerful that simulating it would require harnessing the energy from every star in the universe. No, this isn't science fiction. This is happening right now. Welcome back to the channel. Today we're diving into the absolute cutting edge of quantum computing in 2025 and 2026. And trust me, what's happening behind the scenes is going to blow your mind. Let's start with the biggest headline. In November 2025, a company called Quantinuum unveiled something called the Helios system, and it's being called the most accurate quantum computer in the world. Here's what makes it insane. This thing has 98 fully connected qubits. Think of those as quantum bits with an accuracy of 99.9975%. Now you might be thinking, okay, cool numbers, but what does that actually mean? Here's what it means. The company's chief architect said that if you wanted to simulate what Helios can do using a classical computer, you'd need to harness the energy from every single star in the universe. Let that sink in. But here's where it gets even cooler. Helios isn't just a raw computing beast. It comes with something called Guppy, a Python-based programming language that lets developers mix classical and quantum computing workflows. It's even being used for generative quantum AI, basically using quantum mechanics to generate data in ways classical computers simply cannot, and it works with NVIDIA GPUs for extra acceleration. We're talking about the fusion of the two most cutting-edge computing technologies on the planet, but Quantinuum isn't alone in this race. IBM, Google, Princeton researchers, and even some surprising new players are pushing quantum computing forward at an unprecedented pace. Let me tell you about what happened at Princeton. Researchers there built a superconducting qubit using tantalum on high-purity silicon that achieved a coherence time, basically how long the qubit stays stable, of over 1 millisecond. That might not sound impressive, but it's 3 times longer than previous lab records and 15 times longer than industry standards. Here's the kicker. If you replace components in Google's Willow processor with these qubits, you get a 1,000 times performance improvement. And that advantage grows exponentially as you add more qubits. Meanwhile, IBM is making massive moves internationally. They're opening a quantum computing center in India by March 2026 with their 156-qubit Heron processor. An identical system is already running in Spain's Basque country. And then there's IBM's Nighthawk processor, unveiled in late 2025 and available to users in early 2026. This beast has 120 qubits connected by 2 and 18 tunable couplers that allow it to run circuits 30% more complex than previous generations. It can handle 5,000 2-qubit gates right now, and IBM says they're aiming for 15,000 by 2028. To put that in perspective, the more gates you can handle, the more complex problems you can solve. But here's what's really exciting. Neutral atom quantum computers. These systems trap individual atoms and use them as qubits. Companies like Microsoft, Atom Computing, and Quera expect to deliver small error-corrected neutral atom machines by 2026. Why does this matter? Because neutral atoms offer better maneuverability and parallelism, making them incredibly promising for the error-corrected quantum computing we need for real-world applications. Now, let's talk money, because nothing signals a technology revolution quite like massive investments. In September 2025, a company called PsiQuantum raised $1 billion in a single funding round that brought their valuation to $7 billion. That's absolutely insane for a quantum computing company. And publicly traded quantum companies, they saw double-digit percentage gains in late 2025. D-Wave's shares jumped nearly 15%, Quantum Computing Inc. about 11%, and both IonQ and Rigetti roughly 10%. But here's where geopolitics comes in. According to MIT's Quantum Index report, quantum patents have increased 5-fold since 2014. And get this, China accounts for 60% of quantum patents globally. This isn't just a technology race, it's becoming a strategic competition between nations. Speaking of strategic moves, in January 2026, IonQ announced they're acquiring a semiconductor foundry called SkyWater for $1.8 billion. Their goal? To accelerate domestic production of quantum chips and test 200,000 physical qubits to achieve 8,000 logical qubits by 2028. Okay, so we've got these incredible machines, but what can they actually do? IonQ partnered with Ansys to run a finite element medical device simulation on a 36-qubit system. The result? A 12% speed boost compared to classical high-performance computing, even when handling 2.6 million vertices and 40 million edges. Now, 12% might not sound revolutionary, but this is one of the first real demonstrations of quantum advantage for a practical application. It's proof of concept that this technology is moving from theory to reality. At the University of Chicago, researchers developed a hybrid quantum classical algorithm for identifying biomarkers in DNA and mRNA data. This could revolutionize how we discover disease markers and develop new treatments. But perhaps the most important breakthrough isn't raw power, it's error correction. Google's Willow chip, announced in December 2024, was the first processor where a logical qubit's error rate decreases exponentially as you increase the size of the error correction lattice. Translation: the bigger the system, the more reliable it becomes. That's the exact opposite of what we've seen historically, and it's a massive milestone. Here's where things get really interesting. The future of quantum computing might not be one massive quantum computer, it might be many smaller quantum processors linked together through quantum networks. Spain is investing nearly $12 million in new quantum to build a distributed quantum networking hub. They're developing something called a quantum networking unit that can orchestrate real-time entanglement between separate processors with 99.7% fidelity. Think of it like the internet for quantum computers, using quantum entanglement and photonic integrated circuits for high-speed, low-loss communication between quantum processors. Stanford researchers even developed a cavity array microscope that can read hundreds of neutral atom qubits in parallel. The prototype has over 500 cavities and could scale to thousands for distributed quantum supercomputers. This is the infrastructure being built for the quantum internet of tomorrow. Now, before we get too carried away, let's pump the brakes for a second. A January 2026 report compared the current state of quantum technology to the early transistor era. Yes, we've made incredible progress. Yes, investments are pouring in, but we're still in the early days. Different quantum platforms excel at different things. Superconducting qubits rank highest for computing readiness. Neutral atoms lead in simulation. Photonic qubits excel in networking, and spin defects dominate sensing applications. We still face massive challenges in scaling, wiring, materials, and maintaining quantum coherence. A high technology readiness level doesn't mean we've achieved our final performance targets. But here's the thing, we're overcoming these challenges faster than anyone predicted. So where does this leave us? Quantum computing is transitioning from experimental prototypes to pre-commercial systems with dozens to hundreds of qubits. We're seeing record funding, hardware breakthroughs, early quantum advantage in real applications, and the foundations being laid for distributed quantum networks. By 2026, we expect to see small error-corrected neutral atom machines. By 2028, IBM aims for 15,000 2-qubit gates, and IonQ wants 8,000 logical qubits. This technology will transform medicine, chemistry, finance, cryptography, artificial intelligence, and fields we haven't even imagined yet. The United Nations has declared 2025 the International Year of Quantum Science and Technology to promote global collaboration. Because this isn't just about which company or which country gets there first, it's about solving problems that affect all of humanity. The quantum revolution isn't coming, it's here, and it's accelerating faster than most people realize. What quantum application are you most excited about? Let me know in the comments below. If you found this deep dive valuable, smash that like button and subscribe for more cutting edge tech content. Thanks for watching, and I'll see you in the next one.